Hello everybody, my name is Reinheimer. I'm a research assistant at the Institute for Steel Construction and Material Mechanics under the lead of Professor Lange at the Technical University of Darmstadt in Germany. Today I would like to give you a short presentation about one of our current research projects, which is dealing with the overelastic preloading of high-strength bolt and nut assemblies. First of all, I would like to give you a short introduction by explaining our research objectives as well as the motivation for our studies. I will then move on by presenting some experimental investigations that we conducted a short while ago on rigid end plate joints. And after discussing the results and drawing some conclusions, I would like to end my presentation by giving a short summary as well as a lookout. In general, preloaded bolts have to be checked for over-tightening. If after tightening one bolt or more bolts are classified or defined as over-tightened, this can result in the entire bolt group having to be replaced, which besides costs of replacement can lead to further work which has to be temporarily halted. However, there seems to be a lack of knowledge about the degree of utilization of bolts defined as over-tightened. And furthermore, the assessment of over-tightening, which is given in European specifications, seems to be too general, which led to the aims of our research. We want to gain a deeper knowledge about the influence of an overelastic preloading on bolted connections. And furthermore, we would like to determine a limit value for unplanned overelastic preloading. As mentioned at the beginning of my presentation, we recently conducted some experimental investigations, and we did that by using a 4-point bending test setup with a mid-span moment-resistant joint, as it can be seen here. We wanted to investigate the load-bearing behavior and the load-bearing capacity of rigid end plate joints with overelastic preloading. And in order to do so, we applied different levels or different degrees of overelastic preloading to the bolts, which were M20 high-strength bolt and nut assemblies. And after that, we determined the moment resistant or the moment load-bearing capacity for our joint. So far, we concentrated on two different failure mechanisms as they are described in the equivalent T-stub model, which is found in Eurocode 3. We did tests on mode 2, which describes a bolt failure combined with yielding of the end plates, as well as mode 3, which describes a sole bolt failure. And we provoked these two different failure mechanisms by varying the plate thicknesses of our joint. Basically we used thinner plates in order to achieve a mode 2 failure and thicker plates in order to get a mode 3 failure. Special attention had to be paid to the method of monitoring and measuring the applied preload. We did that by using an ultrasonic measurement system, which is basically using the influence of stress and strain to the time of flight of an ultrasonic wave. So for our test setup, we applied an ultrasonic sensor to the head of the bolt, and an ultrasonic wave was emitted in longitudinal direction of the bolt, and it was reflected at the end of the bolt. Furthermore, the time of flight of this ultrasonic wave was measured, and while the bolt is tightened or while there's any kind of load applied to the bolt, this time of flight changes. And this has two reasons. It's the elongation of the bolt and the acoustoelastic effect, which describes the influence of a stress state in a material on the speed of sound. So the time of flight, or more precisely the change in time of flight delta t, was used as a control parameter and as a target value for the applied preload. This graph on the left side shows the change in time of flight in relation to the strain in our bolt, and the blue line shows delta t just caused by the elongation of the bolt, and the green line shows delta T caused by both the elongation of the bolt as well as the acoustoelastic effect. And we can see that after reaching the yield point of our material, delta T still constantly increases, which wouldn't be the case for the stress or the force, which stays nearly constant after the yield point is reached. So by using delta T as a control parameter or as a target value, we were enabled to define different overelastic preload levels in dependence on delta T. In this table, the experimental program is shown for both investigated modes, mode 3 and mode 2. And we had several test series, including snug tightened bolts as well as bolts tightened to FPC according to the European standard 1090 part 2. And furthermore, there were different test series with an overelastic preload level in dependence, as mentioned before, on the change in time of flight of the ultrasonic wave. And the different levels, which are shown here in time of flight or a change in time of flight, were derived from the maximum change in time of flight, which was determined by tightening a bolt until failure while measuring the time of flight. For all preloaded bolts, we used the combined method, which is also defined in the European standard 1090 part 2. And this tightening method consists of two steps. In the first step, there is a torque defined, and in a second step, there is a further rotation angle given, which for our case, for our bolts and plate thicknesses, was for both modes 90 degrees. So we can see for the highest applied preload, we had for mode 2 330 degrees and for mode 3 340 degrees, which is 240 and 250 degrees above the defined further rotation angle in the specification. Here we can see the experimental results for mode 2, which is the combined failure between yielding of the end plates and bolt failure. More precisely, we can see the moment carrying capacity for each of the mode 2 test series. And it is noticeable that the moment carrying capacity for the test series with the highest applied preload is almost identical to the moment carrying capacity with the snug tightened bolts. So a negative influence of increasing overelastic preload levels cannot be observed regarding the load bearing capacity. Again, for mode 2, the midspan moment and dependence to the midspan vertical displacement is shown in this graph. Exemplarily, there are two test series shown, the one with the snug tightened bolts as well as the one with the maximum applied preload in blue. Again, we can see that the moment bearing capacity seems not really to be affected by the increasing overelastic preload, but we can see a change in the failure mechanism itself. While for the snug tightened bolts, we can see a distinct plastic yield. The yielding for the maximum applied preload is considerably shortened, which means that we are getting closer to a sole bolt failure rather than a combined failure between plate yielding and bolt failure. So that leads to a more sudden failure, which also implies that the failure is less ductile and more brittle. The moment carrying capacities determined for the mode 3 tests show a slightly different pattern than the ones we saw before for mode 2. If we have a look at the moment carrying capacity for the test series with the highest applied preload, we can see a noticeable decreasing tendency. Compared to the test series before, the load bearing or the moment bearing capacity decreased by about 5%. A decreasing moment carrying capacity can also be observed in this graph, which again shows the midspan moment in dependence to the midspan vertical displacement. And again, there are exemplarily two test series shown, the one with the snug tightened bolts as well as the one with the maximum applied preload. And yeah, we can see the decreasing moment carrying capacity for the maximum applied preload, but there is no change in the failure mechanism itself, which makes sense as we are looking at sole bolt failure. That leads me to a short summary of the experimental results we were able to achieve so far. For mode 2 failure mechanism, which describes a combined failure between yielding of the end plates and failure of the bolts, there was no significant influence on the load bearing capacity. However, the failure mechanism itself changes and it becomes more brittle for increasing over-elastic preload forces. That means that the plastic yield of the end plates is considerably shortened, and that leads to a more sudden failure. So the failure mechanism itself seems to get closer to a sole bolt failure rather than to a combined failure. For mode 3, there was an influence observed for the load-bearing capacity, but only for the highest applied preload. And the failure mechanism itself stays unchanged, which makes sense because we're talking about a sole bolt failure. I would like to end my presentation with a short lookout on further investigations we are planning or already doing. Regarding rigid end plate joints, it seems reasonable to do additional investigations focusing on mode 1, which describes sole yielding of the end plate. And we want to add further investigations for mode 2 and 3 in order to get statistically sound data. We are planning and already doing investigations on a larger scope of single-bolted connections. This allows us to easily change plate thicknesses and bolt diameters, and we also want to have a look on dynamic loads. And furthermore, we are doing some numerical analysis which will allow us to extend the obtained results to other geometries and load situations. That brings me to an end of my presentation. Thank you all very much for your attention.